Evaluate the following limits using limit laws. Our first example is the limit as x approaches 0 of -3. First, it's useful to notice that we're taking the limit of a constant. And we have a limit law that is for constants. We say the limit of a constant is a constant. So therefore, this limit should just equal -3, the constant. Now, if you think about y for a second, think about this as a function. You could write this as the function f of x is equal to -3, or you could just think of it as y equals -3. And remember, graphically, y equals -3 is just a horizontal line. So we have this horizontal line here at -3, and we're looking at the limit as x approaches 0. So imagine as I approach 0 from the left, my y values here are all staying at -3. And as I approach 0 from the right, my y values are also staying at -3. Therefore, the left and right-hand limits are both -3. So the limit of a constant is the constant. B, the limit as x approaches 1 of x cubed minus 3x plus 2. So we see that we have a difference and we also have a sum. So we'll use both our sum and difference properties, or sum and difference laws, and we're going to separate this, and we'll compute the limit of x cubed separately from the limit as x approaches 1 of 3x, and then the sum law allows us to rewrite this last one and add the limit as x approaches 1 of 2. So we've rewritten our original limit as 3 individual limits. Then this first limit, you'll notice, is the limit of x cubed. And there's 2 different ways of handling this. One way is to use our power law, since we have x raised to the power of 3. So we could rewrite this as the limit as x approaches 1 of x. We can compute that limit and then raise the result to the power of 3. We'll look at the other way of evaluating this first limit in just a few seconds. Now look at the second limit. It's the limit as x approaches 1 of 3x. So that 3 is a constant multiple, therefore we can use our constant multiple law, which says that we can multiply the limit by the constant. So in other words, the 3 will come out in front and become a product, 3 multiplied by the limit as x approaches 1 of x. Then our last limit is the limit as x approaches 1 of 2. And 2 is a constant, just like we did in our first example. We know the limit of a constant is the constant. So therefore, this limit will be equal to just 2. So now, if you take a look at the limits that we have the limit as x approaches 1 of x, and then we have another limit as x approaches 1 of x. And we have a limit law for that as well. If you think graphically about y equals x, which is just the line with a slope of 1, we know that if we are approaching 1, if x is approaching 1, from both sides as we move along this line, the y values are also approaching 1. So we know the value of this limit is just 1. So this would be 1 raised to the third power minus 3 times 1 plus 2. Final answer here would be 0. Now there is another way of computing this first limit, the limit as x approaches 1 of x cubed. And if you prefer, this works as well. Since we know that the limit as x approaches a of x will be equal to a, and that's the identity law, what we just demonstrated here as we looked at the graph as x was approaching 1. And then we also know the power law, the limit as x approaches a of a function raised to a power will be the same as computing the limit first, the limit as x approaches a of the function, and then raising the result to the power. So if we put these two essentially together, we then know that the limit as x approaches a of x raised to a power would just be the a value raised to the power. So this doesn't have a special name, this particular law, but we do use it as a limit law. And that could be applied up here when we were looking at the limit as x approaches 1 of x cubed, the one that I have boxed in red. So the alternative, if you didn't want to use the power rule there, the limit as x approaches 1 of x cubed, you could go ahead and just say directly that that would be 1 cubed, which would just be 1. And that saves you a step. You don't then have to show the power rule if you don't want to.